Let me start. Okay. So in last lecture, I use first screen. Okay. So last lecture I talked about this microscope. Okay. For microscopy, I talk about this characterization technique or nano characterization technique. I think the basic idea for nano fabrication technique is just use electron, photon, or ion to strike your sample. Okay, let your sample scatter electron, photon, ion. Okay, then you detect the scattered particle. Okay, this is the basic idea for the microscope. For this nano for this microscope. Okay. So I think that there's three types of microscopy. One is optical, another is electron, three types is ion. Okay, I mainly focus on the optical microscopy and the electron microscopy. Okay. Because this lecture is related to nanophotonics, so optical microscopy is very important for us. Okay, so there are three types of optical microscopy. Okay, one is called bright field. Okay. For this microscopy, this sample, okay, this sample was illuminated, we call it wide field illumination, okay. That means that in the total image plane, okay, we receive the scatter field from the sample and the incident field from this lamp source simultaneously. Here we receive a total field, okay. This is called bright field microscope. Okay. Then, if we control the optical path well, we use some equipment to block light. Okay, you can see there's equipment to block light. Okay, you can see the only scatter field from this sample can be received by the image plane. Okay, and the incident wave from the lamp are blocked. Okay, are blocked by this here. You can see are blocked. So they call it a dark field microscopy. So finally, the image plane only get this scatter field. Only get this scatter field. This is called a dark field microscopy. Okay. This is a scatter field. The third method the third method in image plane to get the incident field and the scatter field simultaneously. But the incident field and the scatter field has a different phase delay. Okay, you can see the incident field, the red line and the green line, it has go to this phase plate, but the scatter field it has no phase plate. Okay, so it has some interference. Okay, this is called a phase contrast microscope. This is three types. This is a basic performance for all the microscopy. That's an interesting picture. Okay. The fourth method is very important, called confocal technique. It means only the sample point at its focus plane can be received by the confocal aperture. Okay, this is a black line. You can see this the point source go to this beam splitter and the lens and focus on this focal plane. And then the focal plane will scatter wave go to this confocal aperture. Okay, so they can focus the spatial region of this sample. Okay, this is called confocal technique. But all the technique, if a measure is implemented at a far field. Okay, if all the measures are implemented at a far field, they have to suffer from called diffraction limit. This is a quite an important concept. Okay, so I like to talk about this again. Okay, what's the diffraction limit? Okay, everyone knows that it's for a point source, it's a Hertzian dipole. It has an ionization wave spectrum and a propagation angular spectrum. Okay, for far field, we only can capture this part, this propagation part for far field. This is due to it's a green function. Okay, everyone know for point source, I just put here the E field R equal to minus J omega mu, the diagonal function R prime and J R prime. Okay, D R prime. This is for the near field, far field, and the medium field. So if R goes to infinity, so this equation to change to that, the E R. Okay. Oh, cool. Okay. Let me So, it's for the point source, if the far field goes to infinity, the ER can be written as J omega mu, and the theta theta, and the phi phi is a derivative with a JR prime E minus JK R prime dr prime. So you can see that from near field and far field is a Fourier transform. And the K here so only can be get this kx squared plus ky squared plus kz squared is smaller than is equal to this. It should be satisfy k0 squared. So kx squared plus ky squared should be smaller than k0 squared. Okay, because kd should be real number. So near field and far field is a Fourier transform and a low pass Fourier transform. Okay, so this is a fundamental reason. This is fundamental reason. We only can capture this propagating part and lose the evanescent part. Okay, so this is a basic example. This is a point source. It goes to a slit. Maybe some actually has some kind of spread. Okay, they also have called diffraction limit. Okay, so this is a very important concept. They call angular resolution. Okay, angular resolution for imaging problem. Okay, they said if there has a 2-point source, okay, go to the aperture. What's the minimum angle we can resolve the object? Okay, this is a picture. Okay, this is a picture. So this is theta. Okay, if depending on the shape of the aperture. Okay, for example, for rectangular aperture, okay, rectangular aperture similar to that. The angular resolution for the first bright region just theta equal to 2x because R is far field. Okay, R is very large. You can understand far field. So we can see a 2x at a circle. Okay. So theta equal to, because this is half theta or half of theta equal to x over r. Okay, equal to x over r equal to this circle. Okay. So this is theta is just 2x over r equal to lambda over a. The theta is just called a minimum resolution angle. That means the two objects, it should be at least separate 2x here. Okay. If it's separated much closer, it cannot resolve. It cannot be resolved. Okay. This is called angular resolution concept. They depend on distance. Okay. You can say 2x or r over theta. Theta just depend on lambda, the wavelength, or a is size of the aperture. Okay, size of the aperture. If aperture is fixed, lambda is fixed, theta is fixed. So depending on the 2-point source, depending on the distance between the 2-point source and the screen, we should have separated a different distance. They can resolve that. Okay. So how to calculate them analytically? Okay, let me talk about this model. Okay. Now the problem is here. Okay, how to calculate with the die-degree function rigorously. Okay, this is important thing. Because you learn this, I give an assignment to you. I remember I gave the first assignment to you talk about how to solve this problem. So I just write a code to solve this problem. Okay. So the problem is mathematically just there's a screen. Okay. There's a 2-point source. Okay. So I want to know the field behind. I want to know the field behind this screen. Okay. Behind the screen. Okay. This is a problem we want to solve. Okay, but how to solve the problem? According to equivalent principle, okay, according to equivalent principle, the field behind the screen, okay, the field behind the screen can be represented by the equivalent current at this PEC plane. This is PEC. We are assuming that the screen is PEC. Okay, it's the equivalent current of the PEC plane, okay, and equivalent electric current and a magnetic current at this aperture. At this aperture, because this aperture is air, okay, so I have the equivalent electric current and magnetic current. Okay, so that all the equivalent current produce the correct total field behind the screen, but produce a zero field. Okay, sorry, it produce correct field forward is a correct field in front of this screen, but produce a zero field behind the screen. Okay, this is equivalent principle. Okay, I use J and M to produce correct total field in front of the screen and produce zero field, okay, behind the screen. Okay, so this is equivalent principle. Then I add a PEC. Okay, I add because there's a zero field. There's a zero field behind the screen, so I can add a PEC at this region. Okay, does not disturb the field. Okay, now here the J and M become the impressed current. According to the image theory, okay, the J is reverse, and M has the same direction. So finally, this problem can be changed to here. It's just 2M in here. So J, because J is reverse, cancel each other. Okay, cancel each other. But M is the same direction, so it has 2M. So the final problem, so if we want to know the total field in front of the screen, we just know the equivalent magnetic current is good enough. Okay, if you know this current, we can use the Green function to get this. Okay, so M here is just N cross EI. EI just from the incident wave from this dipole source. Okay, so how to solve this problem? Okay, this is the basic procedure. Okay, first, to get E field at aperture and equivalent magnetic current. So how to get E field at this aperture? Okay, this aperture. How to get E field at the aperture? It's just study Green function. The J omega mu J equal to G0. G0 is the study Green function in free space. Okay, J is a Hertz dipole. Okay, you learn this, so you can get this total field at this aperture. Okay, if we know that if we know this incident field from this dipole source, from the two dipole source, we can know this equivalent magnetic current. Okay, equivalent magnetic current. If we know the equivalent magnetic current, then we use the equivalent principle again. We can get this E field at this observation plane. Okay, so this is the basic idea here. Okay, so first, the EI in this equation is just minus J omega mu 0, the G0 is R prime, and J R prime, dr prime. Okay, this J is a Hertz dipole, a dipole source, a two dipole source. Okay, so first thing, we can use this equation to get Ji at this aperture. Then, second step, we can get this M equal to minus N cross EI. We know the M. The third step, if we know the M, we can know the E at observation plane. Use this equivalent principle again. So it's just gradient cross J 0 R prime dot M R prime dr prime. Okay, this is a basic procedure. Okay, so just use use this Green function twice. Okay, so first the Green function just get this incident field. Okay, just get this equivalent to M and incident field at this aperture. Okay, E AP is E aperture. Okay, then according to this equivalent magnetic current, get the E is a E field at an observation plane. Use a magnetic dielectric Green function. Okay, so we use twice. Okay, Green function. Okay. It's a little bit technical. I have shown this code to you. Okay, in Moodle you can download. Okay, so this here I just draw this result, final result. You can see here. So the distance. This is a basic idea. Okay, this is a basic configuration. So this is two dipole. The distance between the screens is 10 lambda. The observation plane, the distance between the observation plane and the screen is 40 lambda. Okay, it's 40 lambda. This is the basic. The screen is 2 lambda. The screen is 2 lambda. Okay. This is the basic settings. Okay. According to the equation. Okay, according to the equation. This is a 2x. Okay, 2x. This is r equal to 2x over r equal to theta equal to lambda over d, right? So d here is just size. Okay, d here is the size of this aperture. It's 2 lambda. Okay, so it's 2 lambda. So around 1 or 2. Okay, around 1 or 2. Okay, so So the distance 2x is just r over 1 over 2. R is 10. Okay, so it's 5. So x is around 2.5. Okay, it's around 2.5. This is a minimum. Okay, resolution. You can use this equation. So I gave a numerical experiment. Okay. So here first I just separate the 2-point source with 5. Okay. So minimum is 2, 5. I just separate with about 10. Okay. Okay. So it's 5. You can see this is a field. This is a field from the two dipole and it's aperture. You can see, and here you cannot see anything. Okay. You can see this is the two dipole. This is a screen. This is a field here. You can see this is field at aperture. But this field at this observation plane, you can see you can resolve a 2-point source very well. This 2-point source very well. Okay, but you can see the 2-point source is not ideal delta function, but has a little bit spread. Okay, it's spread. So this is intensity here. Now then I shrink. Okay, I shrink the distance. Okay, from 5 to 4. Okay, from 5 to 4. Okay, okay. You also can resolve them, but you can see the peak become emerge. Then I shrink again, shrink to the 2.5. Okay, the limit is a limit. Okay, the limit for this A-magnetic problem you cannot resolve almost. You can see the 2 points are merged with 1 point. Okay, this is from this picture you can see that. Just the distance is very important. Okay, I just say again, this is 10 lambda. This equation is very important. Okay, you can calculate that. Okay. So lambda over d, D is just distance with 2 aperture is 2 lambda is 1 over 2. So 2x just r over 1 over 2. R is just distance from this dipole source to the screen. It's 10 is 5. Okay, 5. Okay. So this minimum resolution is just here. Okay, 2.5. So this is 5. Okay, the 2x is 5. You can calculate that. I use die-degree function to calculate all the field. Okay. So die-degree function is a very powerful technique. You just use them to calculate many things. Okay. Another thing is very interesting. It's just you can understand its results. Okay. You can see this is 2 point is around the 10 lambda, right here. But if the observing plane is 40 lambda, okay, you can see that it focuses around and here is 20. Okay, it's 20. Okay, just how to say that? Oh, this is 5, right? This is 5, so it's 20, just 4 times. Okay, it's similar to ray physics. Let me draw this picture. So they have screen. Okay, it's similar to that. This is okay, something like this. Okay, so here. This distance, initially the first case, is around this 10. This is 10 lambda. Okay. Here is also 10 lambda. So I change to here is 40 lambda. It's 40 lambda. So here is 5. So here is 40, it's 20 lambda. It's 20 lambda. It's just ray physics. If from here, the focus on the points that go here, this is ray physics. You can use very simple, it's a 10 lambda here because it's a distance. 10 lambda over 40 lambda equal to 5 to 20. So you can see your curve, okay? Your curve is 20, it's around 20. You can see this is focal point. Or else you just lose your result. Okay. So this is important. You must know the basic physics. You can check your code whether it's right or not. This is a green function. You can calculate the basic image technique. This is a ray physics. It's a basic ray physics. It's a little bit. Let me draw this better. Go. So, because it's a far field image, so they can use a ray physics. This is green. It's green. It's 2 dipole. Okay. So here it should be focus point. It should be focus point. It's in phase. It's same polarization. So I just do here. I do here. Okay. So here, the distance is 10 lambda, is my setting. Here, here is 5 lambda, is my setting. 5 lambda. So I change to this screen distance to 40 lambda. So this is should be 20 lambda. Okay. So this is the basic, just very simple geometry optics. So you can see here. So my focus point is just around is 20 lambda. Okay. So it's a produce a correct physics. If it's a so you can see here. So the green, I hope everyone can know the green function well. Okay, it's a basic procedure, right? It's a basic procedure. Okay, first they get this aperture field. They get actual field with green function free space. Get this equivalent current. I use the equivalent principle. We can get this observation field. Okay, this is 3 steps. So I spent some time to write this code. I share the code to you. Maybe you can improve them to more complicated imaging program. Okay. This is for microscopy. Then we talk about this how to break this diffraction limit. Because this microscopy has a diffraction limit, so we use a SNOM technique, just near field scanning optical microscopy. So they measure the optic field at a very near field. Typically, it's very close to tip. It's around 10 nanometers. So you can capture evanescent wave information. Okay, I just go to this picture, right? You can see it's 20 or 10 nanometer. The distance between tip and this sample surface is very near. And there has a force between the tip and this atom. So they have some feedback technique. Okay, feedback technique. You can control the distance between the tip and atom very well. I talk about this today for the atomic force microscopy. It's just atomic force microscopy. Okay, so this is for near field scanning optical microscopy. Okay, so I just go down. Okay, another way to break this diffraction limit is with electron, because electron wavelength is very short. Okay, just 1 nanometers. So we can use scanning electron microscopy. Just give the incident electrons and the secondary electrons are scattered. Then we detect the secondary scattered electron. We call the electron microscopy. Okay. Scanning electron microscopy, and okay, the third technique is use full screen. Okay, I use full screen. About is a transmission electron microscopy. Transmission electron microscopy just with the electron incidence and the electron are go transmitted. The electron are transmitted. They just collect a transmitted electron. Okay, called the transmission electron microscopy. This resolution is very high. Okay, can be achieved down to the 1 nanometer, even it's better. So I go down. So today I talk about the scanning, called surface characterization technique. Okay, surface characterization technique. There's 2 kinds of surface characterization technique. One is called scanning tunneling microscopy. Okay, this is a very interesting technique. Another called atomic force microscopy. Okay. We see the scanning tunneling microscopy. Okay, it's due to the quantum tunneling effect. Okay, so typically, if the electron, this is a very different picture for the classical and the quantum tunneling effect. I draw this picture to you. Equivalent principle, just go down. Okay, they said, okay, this has a potential. If they have a potential in here, it has a ball. This is a classical picture. The ball is 1 of mv squared, is kinetic energy. Here is h. Okay, h is just their potential energy just mgh. We know that if 1 over 2 mv squared is smaller than mgh, the sphere cannot go across the peak. Okay. This is classical. This is a fully classical picture. Classical picture said, okay, if the kinetic energy is not high enough to mgh, okay, it's a potential energy, then the sphere cannot go across its peak. Okay, cannot go across. This is a classical picture. But the quantum It's classical. But quantum picture, quantum tunneling is different. Okay, it's a little electron. The electron has a, even the electron kinetic energy, the average value, smaller than its potential. It's a QV. It's a potential energy. See, smaller than the potential energy. It still has some probability. We call it tunneling. It still has some probability tunneling. Can go across this barrier. Okay, this is V. The V is the potential energy. Okay, maybe QV is better. It still has a probability can tunneling to this potential. So the physical picture is something like this. What can see here? It's a tip. It's a sample. Okay, it's a sample. It's a tip. Initially, okay, they has a. If this is far away from each other, I mean they are far away from each other. The electron can be tunneled from this interface. Okay, very small probability. Here they also can tunnel, but they cannot overlap. You can see they cannot overlap. Okay, this wave function. I mean the probability of electron can occupy, they have no overlap. Okay, so it has no tunneling current. But if the tips, it's very near from this sample, very near. Okay, you can see this picture. Okay, very near from this sample. So the wave function, okay, it has overlap. Okay, has overlap. If you add a bias, they can add a bias here. You can see they add a bias. So their potential are not equal to each other. Okay, their potential are not equal to each other. So this has tunneling current. It has tunneling current going across this tip from this sample. This is a fully quantum mechanical. Okay, this is a fully quantum mechanical. We call it quantum tunneling current. It's due to the overlap of the wave function and this distance between the Fermi level. Okay, because it adds a bias, so they can have some current can go across a different tip to sample. This is called a quantum tunneling effect. Quantum tunneling effect is different from the classical effect. Because classical said, okay, if your kinetic energy is smaller than the potential energy, you cannot go across this tip or this barrier. You cannot go across the barrier. A quantum picture said, oh, even your kinetic energy, average kinetic energy is smaller than its potential energy, it still has a small probability to go across this barrier. We call it tunneling. Okay. So if they have two barriers very close to each other, or they have tunneling, they can overlap. Here they can overlap. So they have a current. So this is a quantum tunneling effect. This is different. This is the picture. So finally, the tunneling current between the tip and the sample is a function of the position, tip position, applied voltage. Okay, very important is local density of state. Okay, local density of state. So finally, the current tunnel depends on we call it local density of state. So how to define? It's very similar to photon. Delta omega plus omega I. Something like this, I remember. This is LDOS definition. So what's the meaning of LDOS? Okay, what's the meaning of LDOS? It's how many electrons at this point. Okay, how many electrons at this point? Okay, this means how many electrons at this point. Okay, at this here. Okay, how many electrons at this point? And at this some frequency, at some frequency. Okay, how many electrons at this point at some frequency interval? Okay, at some frequency interval. Okay, it depends on this. Because local density was it. So it's very easy to understand. You can see because this tip, this is sample. You can see only electron around here can go across this tip. Okay, if electron around here they're far from each other, they cannot tunnel. Right? They cannot tunnel. So it depends on local density of state. Just how many electrons at this point, at this frequency interval. Okay. We call local density of state. So this is a basic picture. It's an interesting picture. You can see here. It's a tip. Okay. So first thing, why this STM? Okay, because it's very good. Okay, because first it has a good virtual resolution. Because the current will fall about at all the amplitude. It will increase 1A for 10 minus 10 nanometer AD. if the distance between the tips and the sample will increase their distance, okay, so their tunneling current will fall very quickly, okay, or decay very quickly, just 1 order of magnitude, okay, very quickly. That's the first thing. Another, all the current that focus on this region, you can see it's 90%, it's 98%, okay. So it's almost tunneling current are focused on the tip, between tip and this sample, okay. They have a good lateral resolution, okay. So this is very important for this scanning tunneling microscopy. So they have good vertical and lateral resolution. They have 2 modes. Typically, they have 2 modes for this scanning tunneling microscopy. One mode we call it constant height. Okay, it means the distance between the tip and the sample keeps constant. Okay, this mode only works for the flat sample. Okay, all else the tips will be breaked. Okay, will be broken. So it's the distance between the tip and this surface they keep constant. Okay, they move. So you can form a tunneling current. Okay. Another we call the constant current mode. Okay, they keep the current constant and move the tips top and down. Move the tips top and down. They keep the current set. Okay, because I gave the example. Okay, this is the surface. Okay, this is sample surface. This is T. You should keep the current is constant. If you keep current constant, the D it should be constant, right? It's the D here, but at this position, the D should be something like this, the T. Okay, this is same, almost same, but the T should be changed. Okay, this is the T. This is T. This is the T. Okay. So here, this point and the sample almost not change, okay, because keep the current. Okay, because I said the tunneling current just very dependent on the distance between tip and the sample. Okay, so if you're very far from it, no tunneling current. Okay, if you keep the tunneling current a constant, the tip it should be moved from down and forward, or down and forward. It can move along something here. So this is called a constant current mode for the scanning tunneling microscope. So this is a very nice STM image. You got scanning tunneling image. You can see here. This is 48 iron atom. Okay, you can see it has a very high electron density, right? Because I said that the local density of state depend on the local. Oh, sorry. The scanning, the tunneling current depend on the local density of state. Okay, local density of state that count the number of electron at this point. Okay, per unit frequency. So you can see here, from this picture you see a lot of very sharp peaks. So here it should be have some atoms or some electrons. Okay, so here this is just 48 iron atoms go to a circular ring. Okay, you see this picture because it has many electrons among here. Okay, and so this is a very nice picture. Okay, so this is very good to measure the internal some structure some surface structure. Okay, some surface structure for this your sample. Okay, because you can count the number of electrons. Count the number of electrons at T. It's called local density of state. Local density of photon just count the number of electromagnetic mole at this position. The number of electromagnetic mole at this position per unit frequency. Okay, the local density of state of electron count the number of electrons. It's different. Okay, but it's very similar. Let me draw this equation. Okay, so for photon, the local density of state of photon is just something. It's in free space. It's eigenmole. So K R. Okay. So K delta omega minus omega r, something like this. It's local density of state of photon. Okay, they count the number of electromagnetic mole at this position. Okay, per unit frequency. The electron LDOS, local density of state, is also quite similar. It's a wave function. It's r. square, is delta, is omega. Typically they use E minus EK. Because E is similar to omega, it's h bar omega. It's quite similar. You can see things are very quite similar. Okay. Electron, local density of photon, just count electromagnetic mode. We count electromagnetic mode. Okay, at R per unit frequency. This is the physical meaning. So local density of states or photon just depend on spontaneous emission rate at this point. Okay, how many spontaneous emission rate? I mean how many photon can be emitted per unit time. They can be depend on the local density of state. Okay, here it's just a number of electron. This number of electromagnetic mode. The number of electron at this position R per unit energy. Okay. It's quite similar. Okay, it's quite similar. Okay. This is just for the tunneling current. So, you know, this STM, okay, was invented first. Okay, STM, I mean this pattern. This pattern we invented first. Okay, do this pattern. They see the scanning tunneling microscopy. Then people do the mimic because people know, oh, this definition same, a physical meaning also similar. Okay, what we can construct another equivalent to measure the photon local density of state. Okay, they call it a thermal microscopy kind of thing. They can measure that. Okay, so you can see. I think in physical society, people just use some analogy or similarity. Okay, very similar to each other. They call it scanning. Okay, so I come to this part. So finally, it's atomic force microscopy. Okay, atomic force microscopy. I believe your lab has this equipment. Okay, even in outside lab, maybe in high-phase lab, it has atomic force microscopy. This is very important. Okay, technique. Okay, so you can see it has a cantilever. Okay, they hold this tip. They hold this tip. Okay, the force between tip and atom will bend or twist this cantilever, and this light, okay, from this laser to detector can be changed. So they have feedback to control the distance between tip and atom. Okay. You can see this is a basic picture, the physical meaning here. This is a force between atom and tip. This force is very small. It's repulsive. It has a repulsive, repulsive force. If this distance is far from, it has attractive force. This force is called a van der Waals force. Okay. Every molecule has a van der Waals force. Okay. You pull them very together, has a van der Waals force. Okay. They can be attractive or repulsive. Okay. They have a van der Waals force. This is a force. So they have several different modes. Okay, we have 3 pictures. So one mode is called a non-contact mode. This mode is very safe. Okay, no destructive, no contamination. I mean the tip and the sample, it has not touch. Okay, so we should add some high frequency signal generation to this cantilever. Okay, it will oscillate. Okay, so they can move the tip. Okay, if this tip, okay, because sample is rough. Okay, so the distance between tip and atom will change. So the force are changed. If force change, the oscillation frequency are modulated. Okay, because initially they give the signal generator, they oscillate. Okay, then when they move, they also oscillate, but they are modulation. So this modulation can be detected by a photodetector, give some feedback to control this signal generator. Okay, this is called a non-contact mode. Non-contact mode, I think, is very safe to use because it does not touch this sample. Okay, because the distance between the tip and the sample are very far, so it's an attractive force. You can see it's very small. It's 10 minus 12 Newton. Okay, so this force is very small. Okay, so this equipment is so accurate. They can measure this. Okay, they can sense this very small force. This very small force will affect oscillation over this cantilever. Okay, it will affect them. They can detect with the photo detector. Okay, this is called non-contact. Another is called the contact mode. Contact mode is just touch. Okay, it's a touch of this sample. They have repulsive force because they're very near from each other, from sample and tip. It's about 10 minus 6 and 10 minus 8 Newton. Okay, this is a repulsive force. Okay. You can see here is not necessary to add some oscillatory source. Okay, they just because it's force large enough, they can oscillate this cantilever. Okay, this is called a contact mode. Okay, but a contact mode is very dangerous. Okay, it's very easy to break your tips. So I think the most common mode is called tap. It's the last called tamping mode or tamping mode. That means they tap some your sample, give some time, tap again. Okay, it's some tempo mode. Okay, it's not just directly. Sometimes it will touch. Sometimes it will go above. It touch, go above. We call tapping mode. This is a safe way to do that. Okay. You can see that one layer has a different oscillation amplitude. You can see here, oscillation has a large. Okay, the oscillation has large amplitude. In this region, the oscillation with small amplitude. Okay, they have different oscillation amplitude. They have different feedback. This tapping mode it has tip. It has a make the tip lightly tap on the surface due to scanning. Okay, tap on the surface, so they can eliminate this friction and adhesion force. Okay, initially, if you go here, okay, this is your sample. This is your sample. You go here, they have no adhesion, right? And some friction. Okay. I will do this. But in the third case, if sometimes touch, they can remove this adhesion or some friction. Okay. So this method is very good. They can eliminate the friction and adhesion force. Okay. So they can also it's very safe. Okay. But not easy to break the tap mode. Okay. So this is a basic settings for the atomic force microscopy. I think you should be well trained to use this equipment like a snow, because if before you use them, you should be very careful, because if you break the tip, it's very expensive. Okay, I thought maybe learn 1 year to learn how to use snow. Okay, so be very careful. Okay, I have a pure series. I don't know how to use them. Okay, but I know it's very expensive. You should be very careful. Okay, so I finished all the part. Okay, there's some. Okay. So we have a teaching and evaluation. Like after teaching evaluation, I just summary this course and give a final exam. Right? How to prepare clear your final exam. So please. So you want to use the laptop?
It's fine. I can write it on the whiteboard.
You want to use some internet or not?
No, I just need to write down the link.
Oh, write down. You can use
Oh, maybe
this.
I can show you.
You can use this. This is mine. No, you should pull it down so oil cannot fit. Pull it down. Yeah. The handwriting now is not good.
Sorry. Okay. On behalf of the AAA department, I'd like to make the following announcement. Please go to the web link http://setl.hku.hk, where you should see a list of all forms that you need to complete. Your evaluation will be saved anonymously without any identification. There are separate forms for the course teacher and, if appropriate, the tutor and demonstrator. There are instructions and FAQ link and a link for you to report any missing courses at the web link. So I believe you brought your laptop or tablet and or smartphone. Can you do the evaluation now, like in 10 minutes?
You said SETL.
SETL.
.ht. Okay. Time finish.
I think it's HTTP now. Did it automatically frame it? Did HTTP also?我唔知啊，我都想問點解，我而家冇清標貼嘅，我而家 RA 嚟嘅呢段，我係你老細嘅 RA 嚟嘅，我仲係你老細嘅 RA，我唔使好做啲嘢，因為佢唔知我而家唔係 TA， 我想推嘅，佢仲要唔喺香港冇得推。OK 啊，冇 missing course。佢有啲 course 曲會冇咗呢個 website，你淨係 con 呢啲有得退，咪不如交俾你咯，圖章。即係學校啲嘢就我哋會俾啲人。
你哋整嘅咩？
唔係呢個，其他 con U 個 app。iOS 啊。你驗咗我當全位。應該錄緊嘢，唔係擺上 Coursera 喎。
呢度啫。
哦，
好似 YouTube。
大鑊，咁 cut 㗎嘛？錢㗎嘛？Did everyone finish?
So you have finished or not? Finish and then you need to review about this lecture. Okay, so let me to review. Wait, did you finish? To finish, let me review about this lecture. Okay. So because we have 5 questions in the final exam, so I'd like to review in this Nanophotonics lecture. So I think We have no question in the last part. We have no question in the last part. In nanofabrication, nano categorization, we have no question. We have 5 questions in the fourth chapter. Okay. So in the first chapter, we call this Maxwell equation. It's a Maxwell equation. This is the first chapter. In the first chapter, we call this Maxwell equation. This time variant, this magnetic field will produce electric field. A time variant of the electric field will produce magnetic field. In the frequent domain form, it has current if necessary. In the frequent domain form, it's something like this. Something I talk about this. Okay, this is a Maxwell equation. So this Maxwell equation is quite important. It's for research. We also solve this equation with the boundary condition. This boundary condition, it's just a tangential part is E1 equal to E2. For tangential part, H equal to tangential part is H2. This is for this dielectric material, so 1 and so 2. So for the PEC is the E field, something like this. H field, something like that. The tangential E field equals to 0. Okay, and Bn equals to 0. This is for PEC. This is for dielectric. This is something you learn in for this boundary condition. This boundary condition. This boundary condition is quite important, right? Then you will learn some of the theorem. Okay, the theorem I think is a core part for this lecture. Okay, the first theorem you learn the energy conservation law. I just summary of what you have learned, refresh your memory. Because in the last 5 minutes, I talk about this final exam. Okay, this is not related to final exam. Don't worry about this. But I think I just want to refresh memory. We have you learn. Okay. The energy conservation law. You can see I did not take anything. Right? I just use my memory. I did not take anything. So I hope you can do that. The energy conservation law. The energy conservation law said, oh, this is a closed surface. Okay, the EM will enter into a surface. Okay, it said, oh, 1 or 2 is E cross H conjugate and dot ds. Oh, this energy enter into its surface. That's 2 parts. One is consumed, this nanoparticle. Okay, this nanoparticle. One is consumed by this Ohm loss, the jet of P. It's a 1 or 2. It's dV. And plus, it's a 1 or 4. E dot D minus 1 or 2, the B dot H. This is just exchange energy. Exchange, this means the storage energy is stored energy of E field. The stored energy E field is stored energy of H field. They are exchange energy. That means sometimes they give capacitance, sometimes give inductance. This is a real power. It's a real power, absorption power. Okay. If I wrote this equation in real part, it's real part. And with real part, it's just something like this. This is real part. This is real power. So here we can understand this dissipative power. We also can understand here is source. Okay, is source. It's energy source or energy dissipation. So remember in the last chapter we said if the energy source we have this emitted power. Okay, we can see the dissipative power, also can see the source power. Okay, this is for this energy conservation law. This is one important law you learn that. Okay. This is another is called this momentum conservation law. The momentum conservation law is also said, oh, this is a GF or GT. This is a GM over GT. This is a T dot ds. It's very simple. So this is a field momentum. Okay. So field momentum GF is just c squared over E cross H dot dV. Okay. It's E cross H dV. Okay. This is called field momentum. The Gm over Gt is just F. F just a mechanical momentum, just QE plus QV cross B. This is mechanical. This is a field momentum. A total momentum, add them together, is a Maxwell stress tensor. It's Maxwell stress tensor. This is a momentum conservation law. You this law, you also know why the canonical momentum P equal to mv plus qa. Right? This is in the last chapter. You also learn this is the mechanical part. This is the mechanical part. This is the field part. This is the canonical. It's the moment conservation law. You know this law is we know that the EM field has a force. They can rotation. They can move the object, move the nano object. Okay, they call this a momentum conservation law. Okay, now three law is very important called equivalent principle. Okay, equivalent principle. All I said it has source. J. Okay, I want to know the EM field outside this circle. Okay, I want to know E field, H field outside this circle. And how to know? How to calculate them? Okay, I said, this first thing you can have Green function. Okay, if you know it's a Hertzian dipole in here. Okay, you know the Green function ER. Okay, it's minus J omega mu. The Daily Green function R prime. The JR prime or DR prime. This is the Daily Green function. Okay, equivalent principle said, not necessary to do that. You can measure. You just measure the equivalent current J and the equivalent current M. Okay, along this surface. Okay, the J here equal to N cross H. Okay, the M here is equal to minus N cross E. If we know the equivalent current, this equivalent current, we can know the field outside everywhere. Okay, you said, the E field is equal to is a J, it's a Green function minus J omega mu dr prime, and plus is M dot delta cross G. Okay, this is the magnetic part, it's dr prime. Okay, they said we know the G and M. We know the E field, H field outside this circle. This is called the equivalent principle. They said, this equivalent current can produce total current. This is V2, this is V1. If V belongs to V2, we get its total field. If V belongs to V1, we get zero field. Okay. This is called extinction process. This is extinction theorem. I just use this method to solve image problem. Okay, just use this method to solve image problem. Okay, so this is very important for LED. If you measure the E, J, and H, you can know everything outside. Okay, you only measure the J and H. Okay, if it's a flat plane, this J is M. If I know these two currents, it's a flat plane. It's important. Okay, it's okay. I can use PEC here, the only M remaining, okay? Initially we have 2. If we have J and M, okay, I use PMC plane, use image theory, I use PMC plane, okay, only J remaining, okay, this is PMC plane. Okay, we can use PEC or PMC plane to match only one equivalent current is good enough to calculate everything. Okay, so this is called image theory. So this is the third you learn. The fourth you learn, they call this reciprocity theorem. It said it has a J1 is a current J1. They produce E1 everywhere. There's a current J2. They produce E2 everywhere. Okay, they have two problems. If the media is same, okay, and the media is reciprocal, I mean Imson equals to Imson T. It's a reciprocal media. We have that E1 J2 equal to E2 J1. We call this a reciprocity theorem. Okay, you can check. Using this theorem, you know that for antenna, okay, it's the two antenna, the Z12 equal to Z21. Okay, you can know this kind of theorem. Using this theorem, we also know the couple mode theory. Okay, the couple mode theory. This couple mode theory, they said, oh, it's a coupling between the. If a couple mode theory, I call it A, so B. The dA over dt equal to minus I omega A, then minus omega B. Okay, and dB over dt equal to minus I omega B, and then minus omega A. Here, the coupling between A and B are same. Okay, the coupling between A and B are same. It's also a kind of this reciprocity theorem. Okay, reciprocity theorem. So it's very powerful too. Okay, the finally theorem you learn, they call this the Barbinier principle. Okay, they said, oh, they have screen. The Barbinier principle said, oh, they has a source. Okay, they have a total field E here. So I put the source with a screen, J, it has screen with a slot. Okay, this screen. Okay. They call it E1. Another, the same J, but with a PMC plane. It's PMC. It's PEC. They call it E2. So we get is E1 plus E2 equal to E total. Okay. Now I use a dual principle. I change to this J to Jm, okay, to Jm with some constant. This PMC, I go to the PEC. Okay, E, I go to the H. Okay, so I can change everything. So, okay, something we get is E1 plus maybe some C, H2, okay, equal to total E2. Something like this. This is called the Barbinier principle. With the Barbinier principle, we know that, okay, I give an example for this meta surface. If we have a loop, has a PEC loop, okay, they have similar to magnetic dipole, this M, because it's current here, amperage law is a magnetic dipole. Okay, so if I use this PEC, I give a slot. This slot. It's a complementary structure. This is similar to the electric dipole. It's similar to the electric dipole. You can use the Barbinier principle to understand many things. Okay. This is all the 5 theorem. Okay, in the first chapter. We also learned that there's a very important wave equation is delta Imson 1 delta cross H equal to K0 H. Okay, this is for the eigenequation. Okay, for this another eigenequation, just something Imson minus K0 Imson R and E. This is eigenequation for Maxwell equation. It's eigenequation. Okay. From this eigenequation, we know that this has eigenmode Imson M, Hm, Hm. Any excitation solution, I mean delta cross E minus K0 Imson R equal to I omega mu JR. Okay, this is the excitation solution. The excitation solution Imson R, okay, can be expanded with the eigenmode solution. Eigenmode solution. Okay. The AM here is a very important parameter, equal to something J inner product M and omega M minus omega 0. I have some constant. I can't remember. They said, oh, if it's a current and the J has same polarization, if the current is located at the maximum field point, okay, this mode can be fully excited. Okay, using this method, you can understand many things. Okay, okay. For example, this is a PEC waveguide. You want to excite the TE1 mode. Okay, the TE1 mode. So your location will, or your probe, the location of your probe should be located here, okay? And polarized along same direction. Another, for plane wave, okay, is plane wave. Okay, this is something that if you polarize something here, you can excite this dipole mode. Okay, this is for this nanosphere. But if it's a total mode, if E here, it cannot excite it. It cannot excite it. Okay, cannot excite it. It also due to this eigenmode function. Okay, if you cannot excite it, because this inner product is almost equal to 0. It's almost equal to 0. So this is you learn the photonic crystal. Photonic crystal is some mode, something like this. It's many. Okay, this photonic crystal. This is some mode polarization, something like this. But if you along here, okay, it cannot excite it. Cannot excite. Okay. Also due to this inner product. This inner product equal to 0. Okay. This is all for the part 1. Okay. So I talk about exam. Part 1 we have 2 questions. So the first question about how to write the Maxwell equation. Okay, how to write the Maxwell equation. How to write the boundary condition. Okay, how to write boundary condition. Maxwell equation, boundary condition. Okay, and how to verify some eigen equation. Okay, there's only one question for verify. How to verify the eigen equation? All the eigenmodes are orthogonal to each other. Okay. Okay, this is the first question. Okay, similar to the first question. Okay. Verify all the eigenmodes are orthogonal to each other on the PEC or PMC or periodic boundary condition. Okay, this is first question. Another question about dipole. Okay, dipole. How to calculate the emission power for the Hertzian dipole source? Okay. Okay. How to calculate the emission power for 2 dipole source? Because I give assignment, right? Give imagine theory. I want to calculate the 2 dipole source. Okay. This is the third question. There are 2 questions. Okay. The first question about Maxwell equation and wave equation, and how to verify the eigenmode orthogonal. The second is about this Hertzian dipole. Wait, how to calculate the emission power for Hertzian dipole? How to verify? How to calculate the emission power for 2 dipole? Okay. Okay. So for the chapter 1, about its Maxwell equation, wave equation, and eigen equation. This is the first question. Another is about its dipole. Okay, use the green function to calculate the emission power, something, and this and maybe 2 dipole, how to calculate them. Okay, so this is about chapter 1. We have 2 questions. Okay. Now we will finish chapter 1. Okay, it's easy, not difficult. I haven't given a difficult question. So for the now we talk about the different regime for Maxwell equation. Okay, the first regime is electrostatic. Okay, electrostatic equation is just with the Poisson equation. Okay, this Poisson equation is something like this, or circuit equation, or circuit physics. It's a capacitance, inductance. Everything can become capacitance, inductance, and resistance. This is called electrostatic physics. Okay. While the optical size d is much smaller than wavelengths, we use electrostatic physics. That's very successful is plasmonic sphere. Okay. If d is much smaller than wavelengths, so everyone use the Laplace equation, we know the resonance condition is something like this. For the plasmonic sphere, it's something like this. Okay. This is for electrostatic physics. So second is very important, wave physics. Okay. For wave physics, we talk about this photonic crystal, and for wave physics, the important thing is this picture. This is called K0, K1, K0. Okay, the unison 1 should be larger than K. Unison 1 larger than unison 0. The unison 1 is larger than unison 0. This is waveguide mode. Okay, here. Sorry. This is called K0, this is K1, this is K, this is omega. So this region, this is K rho. If K rho smaller than the K0, Okay, so this region is a radiation mode or leaking mode. Okay, this is the fourth region. And the K rho larger than K0, smaller than K1, smaller than K1. This is a guiding mode. This is guiding mode. If K rho is larger than K1, okay, this is evanescent mode. So this is the basic wave physics. So this is why the reason plane wave cannot excite the guiding mode. Okay, plane wave cannot excite due to the phase matching. Okay. Okay. So the plane wave cannot excite guiding mode. So plane wave cannot excite the, for photonic crystal. Okay, if I truncate the photonic crystal, they have surface wave, they have surface state. Okay, so plane wave cannot excite the surface state, cannot excite the surface state with the plane wave. Okay, plane wave cannot excite the surface plasma. It's metal, 0. Okay, cannot excite the surface plasma. Also cannot excite the guiding mode. Okay, this is all the same physical reason because the K rho should be larger than K0. Okay, so it cannot excite. Okay, it cannot excite. Cannot excite the surface plasma, cannot excite the surface state, cannot excite the guiding wave. Okay, so this is the basic wave physics. So for photonic crystal part, okay, we talk about this. Okay, Bloch theorem. Bloch theorem is a copart, right? It's E, okay, it's X, Y, Z, okay. If there's a Y periodic, I use Y. So X, so Y plus A, maybe Z, equal to E, X, Y, Z, E minus JKE over A. Okay, this is the first form of the Bloch theorem. Another, just X, Y, Z, equal to some E minus JKY, Y equal to some periodic function xy. This is a periodic function xy. It's a periodic function. Okay, along the Y. So it's called a Bloch theorem. We call it Bloch theorem. So for the photonic crystal, for the 2D photonic crystal, okay, you should, this is a photonic crystal. I draw this picture. This is primitive lattice, okay? You should know the reciprocal lattice, okay? The reciprocal lattice just, this is 2 pi of A, this is 2 pi of B. Okay, it's called reciprocal lattice. Then we know the first Fourier zone, okay, here. It's a irreducible Fourier zone in here. It's an irreducible Fourier zone. Okay. Now we can draw the dispersion relation. We can draw this dispersion relation. We call it tau x m. Tau x m tau. Okay, let's draw this dispersion relationship. Okay. It has a band gap. It has a band gap. Also has a band edge. Okay. Maybe something is band edge. In band edge, we have group without C equals to 0. In band gap, the light cannot propagate. It's band edge, the group without C equals to 0. The band gap, the light cannot propagate. This is photonic crystal part. Okay. We also can introduce defect. Also can introduce defect for photonic crystal. I give you an assignment, okay, for this part. Okay. If I introduce some defect, okay, I can introduce some defect. Maybe here I introduce some defect. So this is the band gap. Okay. According to verification principle, the imsum R h delta cross h squared dv of h dv, something like this. So if I increase imsum, okay, increase imsum, the omega will decrease. Okay, it's omega. This is band gap. This is band gap. So something like this, something is a Imson increase. Okay, I increase the Imson, omega will decrease. Okay, I increase the Imson. I decrease the Imson, omega will increase. So this is a band diagram. We have dipole mode, quadrupole mode. Okay, it's kind of mode. It's dipole. I mean dipole mode, high order mode, quadrupole mode. And this monopole. It has many different modes for the photonic crystal. It also can truncate them with surface state. So we have a very famous band diagram, K, omega here. Okay, we have very famous band diagram, something like this, something like that. There's airline. Okay, it has a, we call this surface state. Okay, surface state. It has DE. It has some ED or something, right? It has EE. Sorry, it's PE. Ignited in air, ignited in crystal. Here, we call it decay in air. Sorry, we call this ignited in air, but decay in crystal. We call ED. And because decaying crystal, decaying air, igniting crystal, something like this. It has different band diagram for the photonic crystal. Okay, so because I finished the photonic crystal, the third question about the photonic crystal. So we have several questions. So first question you should remember, how to draw this a boson. Okay, how to draw this boson for this very simple structure. Okay, this is the first question. Then what's the physical meaning of DE, ED, DD, or EE kind of a thing? Okay, or surface state. Okay, it has a band diagram. Okay, what's the meaning of EE, ED, DE, or something? Okay. This is a physical meaning. There's 4 different regions, surface state. What's a physical meaning? It's a question. Okay. You also should know the block theorem. Okay, block theorem. How to write the block theorem? Block theorem. This is for the photonic crystal question. Block theorem. What's the physical meaning for band diagram, D, ED, and how to draw this boson, simple boson. This is for the question 3 is something is the block theorem. Is how to draw this boson. How to know this physical meaning of band diagram. Okay, something like this. Physical meaning of band diagram. It's about photonic crystal. For plasmonics, okay, plasmonics. Plasmonics, we know that plasmonics has a metal-air interface. We know the dispersion relation is something like this. Different from the dielectric, the metal, the permittivity are dispersive. Right? We use Lorentz or Joule model. A very simple Joule model is something like this. That means in the low frequency they are opaque. In high frequency they are transparent. Okay, so this is a Joule model. This is a dispersion relation. How to excite the surface plasma? Okay, excite because it has a guided mode. Okay, so here this airline. So surface plasma something like this. The surface plasma is K is omega. How to excite them? We can use dipole source, right? We can use periodic structure. Okay, we can use prism. We can use subscatter to excite the surface plasma. This is about this surface plasma. Okay. It also, if we have a very thin metal, the two interface will couple. Okay. The D is very small, it will couple. Surface plasma will couple. It's a surface plasma. For local plasma, okay, this is sphere. Okay. The resonance condition is something like this. Okay, this is for Laplace equation. Okay. and it has TM wave. Okay, the TM wave. That means E field is along the R direction. The H field is along the theta and phi direction. Okay, the theta and phi direction. So it has TM wave. It has dipolar resonance. It has dipolar resonance. It has surface charge not equal to 0. It's called local plasma. And local plasma will couple. You put nanoparticle, many nanoparticle. Okay, it will couple. They call this a transverse mode. Transverse mode. It also has a longitudinal mode. Okay. It has a couple longitudinal. In this chapter, I talk about is a phonoresonance, right? Phonoresonance. So phonoresonance is just the meaning of the narrow band resonator coupled to a wide band resonator. Okay, it's a bright mode and dark mode. It's narrow band. It's a narrow band. They couple to some broad band or some continuum. Okay, when they couple, they has this asymmetric spectral line. We call it phonospectral line. Spectral. This is a broad band. This is broad band. This is narrow band. We call it phonoresonance. Okay. This phonoresonance, important thing that you must have this some interesting structure. Very famous structure is something like this. Very famous structure is E field, something like this. It's positive, negative, negative, positive, negative, positive. It's dipole between the coldipole. The coldipole can be excited with a dipole mode. Okay. They also have a very famous structure, something like this. Okay, symmetric. You do a symmetric breaking, you can excite it. Do a symmetric breaking. You also learn the couple mode theory, right? Couple mode theory, very famous couple mode theory. It's a dark mode, or it's a bright mode, is something like this. It's I omega 0 B, okay? Because they also couple to a free space, they have decay rate. It has some S, or R, S plus, okay, the free space. It also has some coupling between the dark mode and the bright mode. But the dark mode only couple to this, this is bright, this dark. Only couple is bright mode. So this is a basic couple mode equation. So if you can remember everything as clear as me, it's very good. I did not take anything, okay. I just use my mind to write that. Okay. So you can see it here. Okay, so let me talk about the exam. The exam, so we have how to write this dispersion relation for surface plasma. Okay, how to write a dispersion relationship for surface plasma. How to excite the surface plasma. How to excite the surface plasma. And for phonoresonance, we have the give the pattern. How to use break symmetry to excite this dark mode. How to produce this phonoresonance by the breaking symmetry. By breaking symmetry. That's this. Okay, by breaking symmetry. That's this question for this. This is the first part. Oh, okay, then we go for the last part, the LED and the spontaneous emission. Okay. So for surface plasma, I say again, it has how to write this dispersion relationship, how to excite the surface plasma, okay? How to excite the surface plasma, and how to use break and symmetry technique to excite phonoresonance. We have some question about this. Not difficult. So for LED and spontaneous emission is the most difficult chapter. I believe the most students confuse this chapter. Okay. This is very difficult. So I think the basic idea is that the for LED the J equal to J0 EV over KBT minus 1. Okay. They call this Boltzmann statistics. If V equal to 0, J equal to 0. Okay. Okay. So this is a Boltzmann statistics. The J0 is just called dark current. It's for LED, dark current. The J0 is Q, G, and L. Okay, at thermal equilibrium, so what's the physical origin of this spontaneous emission? At the thermal equilibrium, we said generation rate equal to emission rate equal to absorption rate. Okay, this is a black body. This is just black body. They said, the generation rate equal to emission rate, absorption rate. The material absorb electromagnetic energy generation electron hole pairs. Okay, emission light. Okay, so this is the reason why the spontaneous emission is very important. How to enhance the emission? How to enhance the emission? Oh, very simple. The gamma is spontaneous emission rate, just equal to a measured part of a trace grain function. Okay, or local density of state. It's also depend on local density of state. Local density of state just count electromagnetic mode. Okay, just count electromagnetic mode. This K count electromagnetic mode at this unit frequency at this point. Okay. So this is local density of state. So it means this is a dipole is atom, they can spontaneous emission photon. But if I put some particle around here, they can enhance the E field around here. That spontaneous emission can be increased. Okay, because they increase the local density of state in here. Okay. So this is the basic idea. Okay, due to a vacuum fluctuation. So in this chapter, I talk about this semi-classical, semi-classical method, and a fully quantum method. For semi-classical method, we use Maxwell equation, classical Maxwell equation. Okay, and plus Schrodinger equation for this two-level system. Okay, this is a B. Okay, this is called excisive. This is A. Okay, B squared, A squared is ground state. So A squared plus B squared equals to 1. If no decay, no relative decay, no other decay. If A squared plus B squared is smaller than 1, they have decay channel. Okay, this is a classical picture. For quantum picture, the Maxwell equation quantized. We have spontaneous emission picture. Okay, we have spontaneous emission picture. Spontaneous emission just by the vacuum fluctuation. This vacuum fluctuation just said the emission power just sit here. Its emission power is equal to absorption equal to generation rate. Okay, they are thermal equilibrium. Okay. So in this chapter we have one question. Okay, so the question is that please describe the basic working principle for LED and the device structure. Draw some simple device structure. Okay, this first question. Another, what's the definition for density of state and the local density of state? What's the definition of density state and local density state? How to boost or suppress local density of state? Okay, so we have 3 questions. 5. We have about LED working principle and the device structure. Then what's the definition for DOS and LDOS? And how to suppress or increase LDOS. Okay, so we have the 5 questions. Okay, let me repeat the 5 questions. Okay, I hope you cannot clearly you cannot pass the exam. Okay, okay. So first question is about this is a Maxwell equation. Okay, Maxwell equation, boundary condition, wave equation, and verify the eigen equation, the eigenmode are formula each other. Okay, this is the first question. Okay. The Maxwell equation, wave equation, eigen equation are also each other. Second question about dipole. How to calculate the emission power for Hertzian dipole? How to calculate emission power for 2 Hertzian dipole? Okay, something like this. Okay, emission power for Hertzian dipole or 2 Hertzian dipole. Because I give an assignment by the imaginary theory to 2 Hertzian dipole. Okay. The third question about the photonic crystal. Photonic crystal is how to draw a Brazon. Okay, draw Brazon. How to know the physical meaning for band structure like DE, ED, DD kind of thing, EE or something. Okay, how to draw this block theorem. Okay, it's a photonic crystal. For plasmonic, we have how to write this disproportion relation for surface plasma. How to excite the surface plasma, and how to produce final resonance by the Brayton symmetry. Okay, something like this. The last question about LED, working principle, LED, and the working principle LED, and the device structure, and the definition for density of state and local density of state. How to suppress or enhance the local density of state. Okay, so I finished. I hope I believe everyone will pass. Okay, because I give all the exam. Okay, so. For this assignment, maybe that you cannot finish. You can give me 1 week, okay? But I extended the deadline with 1 week. Maybe next week you can send to the last assignment, okay? 1 week later. Now today is maybe 14, okay? Today here, you can send me to here. It's okay. It's December 14. You can send the last assignment because I think it's very tight for you. No problem. Okay. If you have any question, you can come to my office to ask about this assignment or my lecture. I'll collect something. Okay. So finally, I hope. Let me say some last sentence because I know this lecture is just a beginning. Okay, just a beginning. I hope you keep reading. I share 3 books with you. I hope you can finish these 3 books in Moodle. Okay. I also hope you can spend some time reading books about Feynman. Okay, Feynman's books. I think Feynman's books will change my life. Okay.
QED.
Okay. You can read Feynman's books. Okay. I hope you can keep studying electromagnetic and optics because electromagnetic optics change people's life. Okay. I believe they will change your life. Not just your capability, but your will and insight towards the world. Okay? Good luck. Okay? Thank you for